Okay, it'll be time to start. Okay, so week 5, almost halfway there. Yeah. So we're going to talk about op-amp design. Yeah, that's it. Before we do that, though, let's first have a quick look at the quiz result. No, the solution. What we get? There we go. So I think the average was about 65 for the quiz, which is probably around common for this course. So let's have a look at what's in here. So first question. So you ask, what is the voltage restriction that you have to apply on the end well here? And because this is a silicon and insulator, then it doesn't matter what happens at the transistor level, it's irrelevant. You just need to make sure you keep that PN junction reverse biased. That's really the only thing. And also you need to make sure that you don't have any ridiculously large voltage on it. So you have breakdown of the PN junction on the oxide. But that is not very often a limiting factor. Okay. This one here, that was probably the killer question. So you have circuit, you have 2 transistors, and this is probably the width we can see here. So we can't actually see the source and drain. And they're connected together with a poly wire, and if you have a high voltage on a poly with respect to the substrate, you can turn that parasitic channel on there. So the question is, what can you do in the layout to fix this? Because what you do in the layout is actually what you can do as a design engineer, not as a process engineer. And what you really got to do there is that you have to increase that distance there. It's probably the only thing you can really do, which means that you've got to put this into not a poly connection, but a metal one connection or something. And there was a suggestion, which is not at all a bad suggestion, that you could put in a P+ block here, because then you convert it. The trouble with that is that if you want to do it in just a layout, if you put in a P+ underneath this poly, you'll get a thin oxide there. That's probably going to break down. So putting in a P+ guard ring around that is a good idea, but you cannot do it without also putting this up in metal. Yeah.
Why can't you push the top bit into the page, sort of push it far away?
Put the top bit into the page?
Yeah. The part that's connecting the 2 gates. That's in the middle. Yeah, that middle bit of metal. What if you push it into the page, away from the 2 end dots spatially? So it's like a big U shape where the bottoms of the U's are connected to the left.
Well, it would probably still cross over the substrate somewhere.
Yeah, but where it crosses the substrate, the end wells aren't there. So.
Well, you've got to get out of the end well area. It starts inside the end well. You've got to get out of that. Then it crosses across the substrate and then gets into the other end well. So you just could create a different pass through. Yeah. So I think you just got to move. This is a normal solution also to these 2. But what you've got to do with high voltage. You've got a problem with high voltage. You've got to reduce the field. You've got to make the distances bigger. That's essentially what you have to do.
I think you mentioned in week 1 we have a voltage stop implementation.
Yeah.
How can we use it?
Well, so the voltage stop implant that is going to be part of the process. Yeah. So it's not something you can do in the layout. It's hopefully there, but maybe it wasn't enough. because maybe in this situation was that you're doing a high voltage circuit, maybe you're having 1.8 volt transistors everywhere, but these sits in the floating well, so maybe this sits 20 volt across that, and that's what the problem is. So, yeah. So yeah, you can't. There's not something you can put in as an extra thing in the layout. If you're a process engineer, you can do it, but not not when you're an IC designer. Yeah.
You mentioned in the first suggestion of creating two wells together as possible. Is there any issues with like capacitance between the well and the substrate?
You will have capacitance formed between the well and the stop state. So when I say this is a possible solution that you join the two wells, this is assuming that these two wells are the same potential, and that's okay. But that's a big assumption.
Also, like the larger area that would take up with that capacitance increase.
You would increase that capacitance, yes. Yes, that's true.
Much of an issue though, because your end well might typically be with like VDD whereas the substrate would be ESS. So would that just act as
It depends on the circuit. Yeah. So if for instance the NREL was at VDD and this was at VSS, having capacitance between the two is a good thing. That's true. Yeah.
That would increase the gate and well capacitance as well.
Yeah, you'll get capacitance between the gate and the NREL, yes. Yeah. No, instead of the gate and the substrate. No. Yeah. All right, let's see what's next. Okay, so next question. You've got to make a chip for wristwatch. It uses a 32 kilohertz clock crystal. And the question is, should we design it in a 180 nanometer or 12 nanometer process? There wasn't really any problems here. The answer is, of course, that 32 kilohertz is you've got another clock yet, yeah. So dynamic power consumption is probably not a problem. Yeah? However, leakages, if this is a wristwatch, you probably want the battery in the watch to last a couple of years. And if it spends most of the time doing nothing, leakage is important. The other thing for this sort of thing is that if it's a wristwatch, the logic in that is probably not very complicated. Maybe you have, I don't know, 1 million gates, and that would be probably, probably not necessary. You can probably do it with 1,000. Yeah? So you don't actually need to have what it benefits through to go to the low line width. So the 12 nanometer just have to have more leakage. It's going to be much more expensive for the area that you actually need. So 180 nanometer, much better choice.
If we use subthreshold region in 12 nanometer, would the power consumption be better in the 12 nanometer?
No, it'd be worse, because in the 12 nanometer, the leakage that you have is going to be much worse.
Even if we use the subthreshold region, we have a lower VDD, very low VDD.
If you lower the VDD, then that would reduce power consumption, absolutely. But because in a 12 nanometer process, you have, even at low VDD, you still have more leakage current, even in subthreshold. Because you have, not even if the threshold voltage is the same, say you were using some super high threshold voltage transistors in the 12 nanometer, you still need to get the gate leakage, which you do not have in 180 nanometer. There's no gate leakage there.
So the power consumption is still much larger than 180.
I would think so. I find it hard to believe that if you have a circuit like that, it's going to be lower in the 12 nanometer because it'll leak a lot.
Yeah, just to decide, is gate leakage like, I would assume it's like 100 times less than channel leakage, or is there any rule of thumb of how comparable they are for something like that in 12 nanometers?
It's very depending on the threshold voltage, what that is. Yeah, and the technology as well. So what you see with gate leakage, if you plot the let me see. So plot the minimum L here, and we're going for, let's say, 180 nanometer down to 2 nanometer or something like that. And we have the gate leakage density, probably, amps per square meter or something like that. You'll see what happens is that it goes up like, it's probably going to be a log-log plot, but probably going to go up like that. And then what happens is that, well, that's too much. So now people change the gate dielectric, and then you get something where it goes down, and then it goes up again. So you have something that kind of looks like that. And every time there's a step there, it's because you change the gate dielectric. This is kind of what it tends to look like. So you make the oxide thinner, but you've got to make the gate, leakage.
Does that make it constant small, or why don't we put everything with the? It's a high K dielectric or something, or like why don't we do that for everything?
Well, you don't do it up here because it is not necessary, and it's more expensive. Because what you have up there, up to about 50 nanometers, you use silicon dioxide. Silicon dioxide is really good material and it's very easy to manufacture. But at some point, the leakage becomes too large and it can't take the field, you can't get the channel controls. And then you've got to change the gate dielectric to something more exotic.
But is this comparable to channel leakage? Or I would assume channel leakage was like way more.
Yeah. It's a good question. It is still, channel leakage is significant, but gate leakage is also something that you've got to take into account. Yeah. It is. I'm not prepared to commit to say which one are they, because it also depends on transistor dimensions. If you have something that's really long and a high threshold voltage, but big, the gate leakage can be by far the biggest contributor to it. So it's kind of, you can't really say. Yeah. So. Yeah. Okay. So next question. So this one was about using unit devices. So we've got a 1 to 2 current mirror here. Can we make it better? The way to make it better is to not use 2 times the channel length here, but using the same dimensions, but making 2 in parallel over there. That was basically what it was about. You can also put in cascodes, that will also help, but this is just a bad starting point for that. So should fix that. Okay. This one here, this question was fairly easy, I think. So how can we make this layout better, and what are the improvements? So pretty much we want to use multiple, instead of 1 long finger, we have multiple fingers in parallel. It means that the gate resistance is going to be smaller, so it can switch it faster, maybe not get hot spots. We're going to have a smaller layout area because we can join, all the drains and sources can be shared essentially, so we can get a significant reduction in area, and that also gives you a significant reduction in the capacitance on the drain as well. The drain bulk capacitance, or gate bulk capacitance, is going to be halved. So that's advantages.
Is there any reason why we do put contacts in there?
Here?
Yeah.
You're not allowed.
Yeah.
That's why. I haven't seen any technology where you can actually put a contact on the gate on top of the transistor. Yeah. It's typically because, you upset the delicate MOS structure, I guess, with the processing. I don't know. Yeah,
It's physically you can put it on the gate if it's off the well. So it must be something to do with the modeling or something, right? Like with the contact on the left, so it must be able to physically go.
Yeah. It's a manufacturing issue, and you get if you put, there's probably also a stress issue. So if you put contact on top of that, you're going to create stress where that is under the gate, and if you put stress, it's going to mess up with your MOS structure. You don't want you build in stress deliberately in that, but you don't want stress that is not intentional in there.
How is the metal? How's it deposited onto the silicon?
How the metal is deposited onto the silicon. So probably with evaporation.
So it must be deposited everywhere.
Yeah.
We etch it off or something. Right?
Yeah. So there's two basic different.
There is metal on the gate, and we etch it off.
When you put but there's the contacts. Yeah. So the contacts are different to the metal. There's a different process to get the contacts done. Yeah.
How do you
So well, first what you've got to do is to etch hole through the insulator that you get, and then you typically plug it with tungsten or something like that.
The insulator protects the rest of the stuff
Yeah.
from that.
So you would.
What do you think multiple fingers and having a square layout improve process variations?
Yes, it does. That is true. That is true. Yeah. Or improve matching, at least. Yes. If you have only one transistor, matching is. Yeah.
I was thinking maybe another reason that you don't put like contacts in above the MOSFET is because maybe the dielectric is long enough under the MOSFET. So
Yeah, it could.
Catch it off, might just damage it.
I could well also be the prey. Yeah.
If your left side is a lot.
Yeah.
lot thicker,
Yeah.
right?
Yeah. If you OH, then it'll be a disaster. Yeah. There's probably many reasons. Yeah. I've never seen a process where you can do that. Okay. Okay. Next question. So, two transistors that burst in saturation, which have the highest drain body capacitance, which is going to be the bottom one there because the drain voltage for the top one is higher, and the drain bulk capacitor has a larger diode, has a larger reverse voltage, so the capacitance is smaller on that. So, yeah, I think most people got that as well. Okay, so this one was about gate leakage. No, sorry, it was about what is the leakage. So if the input here is at 0 volts, where is the leakage path? So with 0 volts, this is going to be off, ideally, and the top one is going to be on. The top one is going to be on, it's going to be in the triode region. So we're going to have a large voltage between the gate and the channel. So we're going to have substantial gate leakage that way. This is going to be off, but only so much off. So channel leakage, or drain source leakage in subthreshold, and this output obviously is going to be tied to VDD. So we're going to have a current pass down there. Not that it really matters for this one here, I guess. There's also going to be, I didn't write this down, but there's also going to be a leakage path between the gate of M2 and the output here, and the gate tunneling, but it's not going to be probably nearly as much as that one up there because it's only going to be sort of because it's off, so there's no channel, so it's only going to be in sort of overlap area. So so gate leakage in M1 and subthreshold in M2 is probably going to be the most important leakage paths there. Okay. And last question was we can write the relative current variance, sorry, due to threshold variation like that. So which is common to do. So if you do that, what does that tell us about how we have to design? Well, quite often when you design, the drain current is something that you specify, you know, for other reasons. Maybe power consumption, maybe you need it for speed, maybe you need it for matching, or sort of for noise. It's normally something that you're not determined for matching. So it would be a common assumption that looking at that, the drain current is fixed. And then that leaves only that parameter left, the channel length, to be something you can influence. These are constants, right? So you can't actually change these. You can change process, but this is not a circuit design decision or design parameter like that. So really, if the drain current is given, the only way you can get the variance down due to threshold voltage is make the transistor longer. It's the only thing.
If you change the length, you change the ID, right?
No, this is under the assumption that you're fixing the drain current.
Yeah.
Okay, so
So
it depends on what you think of as
no.
Okay, so there's it's a good point to make though. It's a good point to make. So if you have a transistor, yeah, and that is given as made for you, you know, it's something that you take from a lab drawer, yeah, then in that case, you know, you wouldn't have anything to play with. The only thing you could do was to increase the drain current. Now, increasing the drain current, what that is doing, if you look at the other equation, is that for giving dimensions, that would increase the effective voltage, which make the threshold voltage less important. So that's why it gets better matching like that. Now, when you're in the design phase, and I think this is, it's important to make that differentiation. Yeah? In the design phase, it's probably better to think about the transistor dimensions as being the free parameters. Because normally that's how you drive the design. And as you might have some specs to do. You need to gain a certain noise performance. You know, if you need to have a certain noise, then that means that, you know, you need to have a certain current. Yeah? So very often the currents that you need to have in a device is kind of the non-variable in determining transistor dimensions. And if that's the case, then it kind of the opposite way, that you can think that as a fixed thing, and the dimensions of the transistor as something that can change. But that obviously only works during the design phase when you're determining the transistor dimensions.
Yeah, because you're like, oh, here I've got this ID that I want to keep the same, but
Yeah.
I want to improve matching, so I would increase both width and length. That would keep ID the same, right?
Yes, that's it's exactly right. So if if you
Yeah, ID the same. But
no, yeah. So if you have the same voltages on the transistor, huh? which I just said that you did. If you have the same voltages on the transistor, and now you want to make the channel length longer, but you want to keep the current, then you need to make it wider as well. Yeah. But you don't have to. If you just make it longer, that's the only thing you do. You drive it with a current source and you make it longer. Then to retain the same current, you need more gate source voltage. So the gate source voltage will have to change. Yeah? So that's a dependent variable now, the gate source voltage, which is a good way to think about it during the design phase and when you decide how things are. It's not necessarily a good thing to think about it when you hook a voltage up to a transistor, because that's your control variable. Yeah. So yeah, it's sometimes you've got to think about what it is that you keep constant in what part of the design phase, and you can get You can get a lot of different results depending on what assumption you make in that space. But I think this is a good way to think about it. Yeah. Yeah.
But in some designs, isn't the L is fixed, the length is fixed, because if you increase the length, then why do we need to use a much advanced process?
If you increase the length, why do you need to use some much advanced process? This is a very good question. It's a very good question. And for the designs where you get a better design if you increase the length, then using an advanced process is a waste of money.
Yes.
Yeah.
Yes. So if you increase length, in the advanced technology, and it seems like you don't need to use the advanced.
No. You're right. You're right. Yeah. Yeah. Well, it depends on what it is you're designing. Yeah. So maybe what you're designing is a system on a chip. And 90%, 95% of the chip is just digital.
Yes.
So that will drive what technology you're choosing.
Yes.
And then your interface circuit, is it just going to have to cope with, being designed in a 22 nanometer process? It's not optimal for what you designed, but that's what you got. That's what you got to live with. It is a very common situation because if you look at systems on chip,
Yes.
most of it is digital, but not all of it.
I know in digital we always use minimal length.
Yeah.
Design. And if we want to reduce the variation in digital circuits across this expression, then if the length is fixed, then what do we need to do is increase should we increase the current?
Well, I guess that's what you will have to do. Yeah. So if you think of the length as fixed, that's not something you want to fiddle with, then you've got to increase the current, which means that you make the transistor wider probably, because if you look at a digital circuit, the voltage is given is not something you can fiddle with. So you've got to make the transistor wider, what is increasing the current. So yeah, that would be what you have to do. Yeah. Yeah. All right. Ooh, we should get on with it. We had so much to do today. So, right, okay. So let's see. No, not that one. No. Okay, so what did we do last time? So we looked at cascodes, we looked at telescopic cascode and Fowler cascodes. We looked at how to bias the cascode, so high swing current mirrors and traditional current mirrors. We also looked at, using different kind of threshold voltages in order to make sure we can have a self-biased current mirror and not use up too much voltage. We looked at improving the gain of the cascode with putting in an amplifier from the source to the gate like that. So kind of like a super transistor, a super cascode like that. That's a very good approach to gaining higher output impedance. One example of that is regulated gain cascode. We're just building in, the common source amplifier here is all you need, but you can't control what that voltage is. That depends on that transistor there. So that's a disadvantage, but it's other than that, it's a good circuit. Yeah. So any questions to any of the cascodes that we did? Okay. We looked at high frequency analysis. So we didn't actually do this because we should, but it's just tedious. So common source amplifier, you boil it down to a small signal diagram that looked like this. Two-node equation. You boil an op-amp down to the same circuit, I should say. It's a two-stage op-amp. You normally analyze using the same circuit. And doing that, we have a couple of things. We can identify the right half plane 0. We can identify the dominant pole and the second order pole. Dominant pole is approximately the Miller, but not exactly. And if you look at a current mirror, we can actually have the same diagram as well. Which is important because up here for common source amplifiers, all these resistances here we have in this small signal diagram is all a sort of RDS type resistor, whereas in a current mirror here, all these resistors is 1 on GM type resistance, so they are 1 or 2 orders of magnitude smaller, so the current mirror is fast compared with the common source amplifier. That's a really important point to note, which is why you can use a common source amplifier to analyze an op-amp. Ignore the current mirrors. We also look at zero-value time constant analysis, which is a method to find the factor to S in a transfer function, in any transfer function like that. And if you make an approximation, first order approximation, you have a single pole system, then that factor is 1 divided by your angular frequency. And we can find that by taking all the reactive components, which is on the chip capacitors normally, and find the resistance that would look into. And then sum them all up, and then we have a time constant. So that is really what we did last time with that. Is there any questions to this? Okay. All right. Okay. Let's get on with today's topic then. So we're going to look at advanced op-amps. So, okay, let me just, before we start there, I really want to show you a two-stage op-amp. I think I can be faster than drawing it. If I go here. Go. Okay. So your typical two-stage op-amp with a differential pair with a current source load, also a long-tail current source, and a current mirror load here that feeds into a common source amplifier, which has an active load as well. So a current source like that. You have the compensation that sits. A Miller compensation that sits from across the common source amplifier, and in order to get rid of the right half plane 0, it's got a nulling resistor in series with the compensation capacitor. So this is all. That's the undergraduate material. Yeah. So now comes the question: how can we make better op-amps? And this is not a bad op-amp. It's not a bad op-amp, but we can make things that have better properties, at least in some way. So I'm going to introduce you to a few different kind of op-amps. So the first one is the current mirror op-amp. Current mirror op-amp. So what you do with this one is that you have a differential pair as per usual, your input voltages, and then you essentially just mirror around the outputs from the differential pair, the two outputs from the differential pair here. There's bias voltage here, V in 1, V in 2, using a couple of current mirrors. So like that, current mirror over here, another current mirror down here. So this is probably ground, VSS, whatever you want to call it. Okay, so that's the op amp. So, so really, the current that flows in this branch here is then flowing, current flows down in the right-hand branch here is going to flow out of the output. The current that flows down in this one here is going to flow down all the way to the left, and that's going to flow into this transistor here. Right? So this sort of structure subtracts the two currents in the output node rather than having one current mirror that sits up there. Now, if we want to have gain, then what we're doing is we're putting in cascades. So you've got to get rid of that one there and then put in cascades here and here. So let's call it VB1 and VB2. Okay. And this is your current mirror op amp. It's a cascade. So it's a cascade op amp. Very often you call it also an OTA, so operational transconductance. Transconductance amplifier. So you'll very often see in papers that the term OTA is used pretty much as a synonym for operational amplifier. Now they are different. So if you look at how we get gain here, we have really taken the difference in current here, and that is what is injected into this point here. So the difference in current is the transconductance for the differential pair times the input voltage. And you dump this current into the output node. The output node here has a very high impedance because you put in the cascade. So now the gain you get from that is GM-RDS squared or something like that. You should probably work it out. So we have, the current here. Let's call it I2 and I1. We have I2 and I1 and I1 here. So that current there is I2 minus I1, which is also equal to GM times Vin, where Vin is the difference between, so that's V in 2 minus V in 1, I guess. And GM is that's for the differential pair here. The output resistance we get here, that way up, there's going to be something like RDS for that one, for the top transistor, times GM RDS for the cascade transistor. And then the resistance we get at the output is we get the same resistance down here. So that's also RDS times GM RDS, if all the GMs and RDSs are the same. So the output resistance is about a half times GM RDS times RDS. Okay, so you can see that the gain here that we have is going to be the current that we have flowing at the output and then times the output impedance. So it's going to be a half times GM RDS squared. So this is actually better than the two-stage amplifier by 6 dB, because in a two-stage amplifier what you have is you have GM times RDS on 2, and you have that whole thing squared. Because you have two stages, you get approximately that same amount of gain, but that half there is not squared, so you get twice again on this one. Yeah. Now, you can also, just put in two cascodes. These two cascodes that are put in there is what matters for the purpose of the gain. If you want to do it nice, you probably put in cascodes on here as well. And then when you do that, you put cascodes underneath here. So you have what's really a high swing current mirror here and a high swing current mirror here. Just, you might as well, you already had the bias voltage. Transistors doesn't cost anything. So you just get a better, mirroring effect of that. So, and then, once you add it, you probably make this bottom here into high swing cascade mirror as well. Yeah, but yeah, it doesn't change the operating principle at all. So this is a very good amplifier. So it has the same gain as a two-stage amplifier. Now, what you sell though is that you have to have more voltage across this at the output for it to be in operation. Okay? So that's the cost. And of course, what we have is that the output impedance is very high. Now, having a very high output impedance, well, that means it's not actually a very good operational amplifier, voltage mode operational amplifier, because the output of that should be a voltage. And if you have a high impedance, a voltage is not a good model for what happens at the output. No? It has a very high output impedance, which means that we really have a current output, which makes it a transconductance amplifier. Voltage in, current out. That's a transconductance. Yeah? Now, what makes it operational is that just like an op-amp, you are normally using this in feedback. Now, very often on chips, you don't want to use resistors in the feedback because, one, that current flowing in those causes power dissipation. And also, it means that you've got to make your amplifier so they can drive these resistors. And that's often not necessary. You can use capacitors instead. Now, it's a little bit more fiddly, but that's perfectly fine. They don't add noise, and you don't have to drive it. So it's very, very common to use OTAs on chips instead of op-amps. That is your default component, even if it looks a bit funny. Yeah. Now, the other thing that's very nice about this is that this is just really what you should think of as a single-stage amplifier, because we only have gain in this one node here. Now, that means that when we close a loop, we only have one node, one pole in the feedback, rather than two. If you have two poles in the feedback, then it can become almost unstable. Yeah? And that's no good. And then we've got to put in Miller compensation, and then that makes it unstable because of the right half plane zero, and then we've got to put in lead compensation and stuff. Here, we just put in load capacitance, and that is essentially your compensation capacitor. Well, it is your compensation capacitor. So the capacitor here, CL, so that's V out here. This is also your compensation. So that's two reasons why you want to use Miller compensation. One is that you don't want to put a capacitor that is in a narrow farad range in one of your nodes to make that the dominant pole in the system. So you use a Miller effect to boost up your capacitor. You can make it smaller by the amount of gain you have in your second stage. Now, the other thing that with the Miller compensation does is it does pole splitting as well. So your second pole in the amplifier moves up to much higher frequencies. So that's a kind of similar to that. So the gain bandwidth that you can achieve on this is probably not any better really than what you can achieve with a two-stage op-amp. But what is really nice is that if you put in some extra capacitor, you're just going to load the only node that's in here. It's going to make it slower, but it's going to make it more stable. Now, for a two-stage op-amp, if you put in too much capacitor and a load, you can make it unstable.
So, you say that's the benefit of Miller compensation is that, like, on chip we don't have to have as big capacitors, like for the same
Yeah.
station for this, my load capacitor would be a lot bigger.
No, they will be about the same. Yeah, because if you want to put the dominating pole at the same frequency, because the impedance of this node here is what you get in a single stage amplifier. The impedance you get is about RDS, well, probably half RDS. Okay, so in order to get a large, low pole, you need to have a large capacitor to get that. But the impedance is GM RDS higher, which is the same effect you have from the Miller. So GM RDS is about the gain you get in one stage. So the capacitance you need here is about the same as the capacitance you need in a two-stage amplifier. Yeah. So, yeah, that makes this a very nice amplifier.
And you say the gain is only at the output. So what about the GM on your inputted pair, or if we put cascodes throughout? So none of those things provide that.
These are low impedance nodes. Yeah? So the impedance level in all of these nodes here is a die-connected transistor. So look into the impedance there. That's about 1 on GM. On this node, and that node, and this node. Yeah?
And if we cascode it, it's even less.
And if cascode, it doesn't matter, because if you put in a cascode underneath here, then it's still the same impedance level in that node.
I thought we cascode to just where the impedance.
You cascode at the output. So if we go, yeah. Okay. Let's have a look at that one there. Yeah. So, so the impedance that you look into in this node here, this is the source end. So you look into the source here, which has an impedance of about 1 on GM. The impedance of this node here, that's determined by, well, if you move this voltage about, you're going to modulate the gate source voltage of this. The current response is going to be GM for that. So the impedance you look into here is also going to be 1 on GM because of that transistor. That's the same node as that one. And the impedance you look into here, well, in principle, it actually depends on what happens up here. If you have a zero load, you're looking into 1 on GM. Other than that, it can be a little bit high impedance, but that is a really high impedance node, the output there. The other ones are lower. Certainly at the input side, these are still 1 on GM. It's not actually important whether you put in this transistor or not, in terms of the impedance levels at the input. It's not changing anything.
So anywhere eyeball for the impedances? It all looks the same when I was looking it up. I could be able to point out what's the higher low impedance nodes as far as I can see.
It helps if you draw in the source error.
Yeah.
So it is probably it's probably a good idea to go through and analyze what happens at a common gate amplifier. Which is what happens here. What is impedance looking into that on the common gate? Which is what this is, and what impedance is looking there.
And looking up into a PMOS is different from looking up into a NMOS. I think that's what
Yeah, so it's about the source, whether you look into the source or whether you look into the drain. Yeah. So there, the source is the low impedance point. Yeah, because what you probably should think about is that if you grab hold of that voltage and you wriggle it about, what's going to happen to the current flowing there? If nothing's going to happen to the current flowing there, then it's a high impedance node. If you're going to modulate the current, because if you wriggle that node around, you're modulating the gate source voltage of a transistor, that is going to be a low impedance node and 1 on GM type of thing.
And also, I think Harrison, he talks about dueling current suppliers. I don't know if you come across that in the specs book.
What?
He talks about dueling current suppliers, and that you should never design an op amp that has two current suppliers pointing at each other, because one will always be a little bit mismatched, and then if it's a tiny bit, it'll drive the other one to.
Yeah, we're going to get to that later today. Yeah. Okay.
And the last thing was, how do we bias the cascodes in the OTA? Do we just pick a voltage, or is it
Like that. Just like we did last time. So this is how you bias a cascode. The common thing is to use a wide swing cascode. And what you want to do is you want to make sure that as much as you can, you take process variation out of the equation in doing that, what is normally like that. You have some kind of bias current coming in. Going to talk about later today how to do that, so also in more detail. But essentially, if you have a current source, that is how you start with that. Yeah, so if you have one current source and you want to use that as your reference current, you generate the bias current like that with sizing this transistor. And that's a bias current for all of your entrance transistors like that. And you can do the same with a P. So you put that into a current mirror, you mirror that up, and then you have the same structure and do the same thing for the P. Yeah. So, yeah, okay. All right. I'm going for time. All right. Let's see. We should probably have a break here, shouldn't we? Yes. Okay. I've still got about 200 circuits to get through today, so yes. But we still need our breaks. Let's break and then meet again. I'll give you 9 minutes. So 7:05. Okay.
但其实一般情况都是用那个比例点。
Yes. 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 If you have two gain stages, you probably do need to do a Miller computation.
But for OT stage, it's fine. Like this one can be considered a two-stage OT, or just
I consider the one stage okay because there's only gain in 1 point. You only have 1 point in the circuit where the gain happens. That's at the output node. All the other structures is riding around the current at low impedance levels. Yeah. Yes, they're DC voltages. There's no, yeah.
But if the DC, this part contains some kind of couple, is that a noise or something can still, or AC still can couple in?
It can. That is true. That is true.
But as long as they do not have some kind of feedback, it's fine.
Yeah.
Actually, the reason why this one doesn't matter for I2 as the question system he asked, I2 and I1 maybe have little mismatch, this is fine because they have feedback from the diode, the current meter at water.
So if there's a mismatch between I1 and I2 at the output node, then that will be equivalent to you having an offset output current or an offset input voltage. You can then adjust the two input voltages a little bit such that those two currents are exactly the same.
The voltage, VBI.
No, V in and V2, the input voltages. you will have an issue with mismatch. So I1 and I2 are not going to be the same. But that is equivalent to having an offset voltage in the amplifier.
The OT itself, the bottom current mirror and also the mirror can be introduced what's called the negative feedback to compensate the mismatch between.
You're thinking of a fully differential amplifier now. Yeah, but this is on a fully differential amplifier. You have two nodes you've got to control. So you have two-dimensional problem. So one of them you can control with an equivalent input offset voltage that is fixed by the negative feedback, or all negative feedback. But if you have two nodes, you only have one loop there. You've got to have another loop to control the other dimension.
Because then the core mode cannot be calibrated by
Yeah, yeah, normally.
But this one, core mode, yes, actually, because the core mode, the left and right is activated symmetrical.
No, they're not symmetrical.
Oh, so there's no core mode, it's not core mode.
Well, there's no common mode at the output. There's only the signal. Yeah, yeah. So that's a more complicated issue. Obviously, yeah. You should read the textbook. Yeah. No, it does. So do expect that people read the textbook. Yeah.
How do you actually choose VD1 and VD2?
Like what we did last time. Yeah. It's so if you put in, so if you replace this one here with a high swing current mirror, this is what we did last time. Yeah, and then you bias it just like you did last time. All right, time to start again. so I have made a small variation of this circuit here. So I have put in, we've got a cascade current mirror here, and then we have something at the top that I have also made into cascade, but I have not made these connections and made this a bias point instead. So we have a circuit which now looks like this. Okay, so we have your current mirror down here, and then you have essentially two cascaded current sources up there. Okay. I probably should put in, I don't know. Let's just put in the sources as well. This right color. So this is the source here, and the source there as well, and the source is here. Okay. Right. Okay. So if you want to take this structure, there's another way we can make this into an op-amp by attaching a differential pair. And we can do that like so. We have a differential pair. Oh, actually, let me just move this a little bit to the right. I think I want to do that. Sorry. Oh, can I? No. No, I can just do like that. Oh, that was lucky. Okay, there we go. Right. So differential pair. Pop this in like this. Just going to put a current source at the bottom here, and then we have the two inputs here. One goes and connects there, and the other one goes and connects over there. So this is a folded cascade OTA. This is the output voltage, the out. And we also have the load capacitance sitting here, as before, which is also the compensation capacitor. Okay. So the way that this works is that the current that flows in the two branches here, let's say I1 there and I2. The current flows down here. Well, it can't, the small signal current, that would have to flow this way here. It flows into the, if it flows out here, it can't come from up here, small signal wise, because there's a current source, so the small signal current going that way there. Okay, so there's from a small signal perspective. Well, from a small signal perspective, that one up there is a constant current source, so that's an open circuit. Now, if you look at what happens from a large signal perspective, if you add it onto that, then physically the current had to flow from top to bottom. Yeah. So. These ones here, as a current mirror. So the current that flows in here flows out there.
Is that a load or
I don't. Well, yeah. I don't want to call it a load as such. It's just, I guess there is some load somewhere, but it's not really used as what you would have in a two-stage op-amp with a differential pair. I guess you could call it a load. Yeah.
And what sets I1 and I2? VB1, VB2, or VB3?
VB1 is setting, that's a bias voltage that sets the gate source for those two top transistors. That sets the current. VB2 and VB3 are cascades. You can recognize this as the top ones here, the two P transistors, are Fowler cascades for this differential pair. That's why it's called a Fowler cascade op-amp. So yeah, these two are Fowler cascades. So yeah, the small signal current going that way. So that means that I lost my pen. What did it do? Ah, it fell on the floor. Oh, yes. I saw that. I thought, I remember that. Okay. All right. So this is I1, small signal flow this way here. So that will flow that way in the current mirror. So we have I1 flowing that way in the current mirror, whereas I2 will have to flow this way here. In there. So what we have flowing out here is going to be I1 minus I2. So this is the same thing as what we have up here. These are also large signal currents, but you can also think of them as small signal currents. So essentially what happens is that we're subtracting the two currents, the two small signal currents from the differential pair in the output node here again. So why would we want to do that? Well, it has similar properties as a current mirror op amp, but there is a significant difference, and that is if you look at the total current that you have in your op amp, then what you have, you can increase, I should say this, you can increase the current from here to here, by making this a 1 to 2 current mirror, for instance, and the bottom one a 1 to 2 current mirror. If you do that, you get twice the current out here. That actually means that by sizing this up, you can get a higher transconductance that you have. Now, if you do sizing in this one here, it doesn't actually matter. Now, if you put in more current in these branches here, so if you increase I1 up here and you put more current in here, that differential current that flows in the diff pair there is not going to be affected from that, because one of them flows directly to the output like that. It doesn't go through a current mirror after that. So this has a consequence that if you look at the total amount of current that you have available in the op amp, very often you are restricted by how much current that you're allowed to spend, battery life or whatever. Then what you normally do in the photocascode here is that you put in not very much current over here. You put most of your current in a differential pair. Okay? Now, if you put most of your current in a differential pair up here, of your total current, put most of the current in a differential pair, that would mean that you're scaling this current meter down. Yeah? Maybe you have, 80% of the current here, then it's only left 10% of the current over here. So that's got to be in a 5-to-1 current mirror or something like that. And now what we do is we reduce the gain because we're scaling down the current. So you don't do that in this op amp. Now the advantage that you have for the photocascode op amp is that you can put most of your current in the differential pair, is that the thermal noise that you get from your system is dominated by your two input transistors. It's dominated by these ones here. And the more current you have in your differential pair, the more current you have in these, the lower the thermal noise. So this structure is better from a noise perspective. Because you get, for the same gain, whatever, you can just put all, most of your current here, and you get good noise performance. So that is handy. It's good for noise.
Is the output swing better?
The output swing would be the same, approximately, because we have to have, if you use wide swing cascode current mirrors everywhere, we've got to have two saturation voltages from the positive supply and 2 saturation voltages from the negative supply. That's the same in both of them. Yeah. So the downside of putting most of your current over here is that you have essentially less current, because most of this bias current up here flows into the differential pair. There's not a lot of current flowing at the output here, so that means that you have less current to charge and discharge this capacitor. So the slew rate of this is going to be not nearly as good as the other one. So the current mirror op amp is better for speed, and the photo cascode is better for noise. Yeah. So this one here, speed. This one here, noise. All right. What else can I say? That's yeah. The way you choose the current that flows in your current mirror here is just by how much of the current from the top here do you pull out here. The rest will flow in the current mirrors.
And I guess the lower limit of I1 is when the noise starts to become bigger than relative pair.
So I1 has to be larger than I2 on 2. You need to make sure that I2 and 2 flows here in each of these branches, and this I1 comes down here, and we got some of that I1 has to flow on this one here to keep this biased. Yeah. So.
Does it save current overall then if it still needs to have if I2 is
does it save current overall?
I thought the benefit here is that we can put most of our current into I2, whereas it seems like it's only half. And I'm sure I can compare it to the first circuit and see.
So we can't put all of the current in I2. So if you make I2 equal to 2R1, then there's nothing left here. Yeah? So that won't work. Then then there's not biased.
And the total current here is I2 plus 4 times I2. Is that right?
Well, the total current is 2 times I1.
Yeah.
Yeah.
Which at minimum is 4 times I2.
Yeah.
And compared to the circuit on top.
No, and the minimum is got to be I2. Got to be larger than I2.
Yeah. Compared to the line above, it's just 2, 1, 1.
If you look at above, then what we have, I2 is a long tail, so let's make this one here I2, yeah? And then we can scale it here. This can be 1 to K. We can also make this one here 1 to K, so 1 to 1. I don't know if that's the best one. Sometimes you do only scale up the output, becomes slightly asymmetrical, but it saves current. So then what we have over here is going to be a half I2, if you have that scale, and the current that flows over here is going to be K half I2.
1 to 1. So in total, the current here is 2 I2.
Well, the total current spent up here is going to be, so you get 1, 2, 3 half I2 plus, so 3 plus K half I2.
And if we assume K is 1,
If you assume K is 1, then it is going to be equal to 2I2. Yeah. But yeah, so the premise is, if we want to have most of our current in the diff pair, because that's where we get the best bang for buck for noise. If we have most of our current on the diff pair, what we've got to do is to make k smaller than 1. And then probably make this one to k as well. And if this is smaller than 1, then the gain from here to here suffers by k. We're scaling down the current driving capability for that. I'm scaling down. Now that doesn't happen in the other circuit because of the structure.
Right now it's a half, and the one below it's like a
Yeah. So, yeah. So all, this doesn't suffer from, from the gain point of view from putting current in the diff pair, whereas the other one does. So, so normally in the other one you make k larger than 1, larger than or equal to 1 for sure. You don't make it smaller. Whereas here you'd normally make, you might have 80% of the current in your diff pair or something like that. Okay. Now, the other thing we can do with this is we can, let's move this up here, is we can make, let's call it V2, V1. We can pop in, okay, so this one has another advantage actually. So you can see in this structure here, the largest voltages we can have at the inputs is going to be less than the power supply. Yeah, so to a first order, we have a gate source voltage between the power supply and here. So let's say the threshold voltage plus a VT, and then we need to have a threshold voltage across here, and then we have a threshold voltage plus a VT. So we really probably sitting about 1 VT shy of the positive supply and how high the common mode can go here. So if you go and we look at the furthed cascode here, that's not the case, because we can bias this as a wide swing cascode, so the voltage on the drain here is going to be just one effective voltage below the positive supply. So this can almost, if the threshold voltage is positive, this can go above the positive power supply, easy. So this has a much better common mode in terms of going high than the other one. Going low, they'll be the same. However, what we can do is we can pop in another differential pair, being a PMOS pair, like this. PMOS pair. And then we can pop in that in here. Like so. So this is really quite interesting because these source points here, these are perfectly good inputs to this current mirror. It doesn't have to go in here. We can put in signals in here. So if I push a current into this node here, that current is going to cause this voltage here to increase, because if pushing a current into that way is high impedance, this is 100 GM, so the current will flow up here, it will flow into this node here, that's going to raise this voltage. So if you push a current into that, the gate source voltage of this one here will actually increase to accommodate that current. So you're pushing a current into that, going to increase that voltage. Well, that means that we're going to have more current flowing into here. So it has the same effect as putting in a current here. You can put it in current here, this still comes out like that. On the other hand, if we put in a current here, well, that's going to take away from the current that goes in here. So that current, or you can see pushing in current here is going to go this way, whereas putting in current here is going to go that way. So this looks like you can subtract the two currents on these nodes here rather than doing it up here. Which is funny, but very useful. Okay, so let's have a look at, let's call it I3 and I4 here. So I3 going this way here, then it'll go up here, I3. And I4, if you push it in there, that is going to go in there, and that means that that's going to go this way here, I4. So what we have at the output is we now have plus I3 minus I4. Sorry for the very small writing here. Okay. Now, the interesting thing is for the PMOS common mode input here, that can go below the negative supply because the voltages around here is going to be about 1 effective voltage across here. So these ones here can easily drop below the negative supply. Now, if you now connect the gates up together in such a way that they don't cancel, they will add together, and now we have a rail-to-rail input stage. Let's see if we can do that. So we want to have, so which one is larger? If I1 is positive, so V1 is going to be the positive input and the negative input here. So if we have something flowing, I3, if this is higher, then we're going to it's going to be plus I3. So we want to have minus there and plus there. Is that right? So that means that this should be V2 and V1. Is that right? So if I3 is the biggest, then that flows out. So V1 bigger than V2. Is V1 bigger than V2 on the first pair? I think that's right. Yeah. So, yeah, if you swap them around, they cancel at the output and the gain is 0. So you just got to make sure that you work out the right way. Yeah. So rail-to-rail input, which is another really useful thing. Okay. Yes, so I think that's probably what we want to do now.
We need to put them in the middle of the MOSFETs. We can't put them, where V out is.
You could put them on there, but then you don't get the benefit. So if you put that input up here, then suddenly you need to be, you're in the same. What is loading this transistor is a diode-connected transistor, and you have the same problem. You can't reach a negative power supply. It's the same as condition. But this is why it's so nice that you can go in there. There's nothing wrong with going in at this point of the current mirror, and you have it's a good place to go into the current mirror. For a small signal current, you need to have bias current going in it, so you need to have another current source up there somehow that keep it going. But for a small signal point of view, you can get current in there. Yeah. Yeah. Oh.
Actually, for both the input pairs, the threshold voltage should be like that higher is too small. Threshold voltage is too small, then cannot touch the real, right?
Well, as long as the threshold voltage, in principle, if we look at having the same effective voltages of all the transistors, which is simplified, but if you have that, then the threshold voltage, the threshold voltage need to be higher than an effective voltage. In order to do that, but this is almost commonly the case for that one. That's true, but it's not hard to achieve. So you had a question?
Yeah, I'm struggling to understand the common mode. So the rail-to-rail input part. So how for that I4 that's being injected into that NMOS that cascade current mirror, why can we have that voltage be negative?
No, you can't have it being negative. So what I've drawn here is a small signal current.
I think V1.
V1. This is the negative input, V2 is negative and V1 is a positive input.
Yeah, so, or I guess I'm trying to understand how V1 can go, why it can go to the, why it can process the lower voltages.
Well, I can process a lower voltage.
Because of the PMOS.
For the green.
For the PMOS, okay.
Yeah.
So for PMOS, the source gate voltage is a threshold voltage
Yeah.
plus an effective voltage, minus a numerical effective voltage. Yeah? So if the threshold voltage is minus 0.3 volt, whatever, then you probably have a source gate voltage of maybe 0.4 volt. Yeah? With a 100 millivolt effective voltage.
Will turn on. Okay.
Yeah. So you have a lower voltage there than you have there. And the voltage you need to have here is an effective voltage. Or the absolute value of the effective voltage, this has to be lower. The drain has to be lower than the source.
Yeah.
Okay, by, let's say, for the sake of argument, 100 millivolts. It's a bit low, but let's just say that. Right? So that means that you can also see that you're not allowed to let the drain be higher than the gate by more than a threshold voltage for it to be in saturation. That's another way that you can write it. Yeah? But the voltages you have on a drain here can be, let's say, this is determined by the bias voltage you have here is pretty much a constant voltage. So if you bias this as a wide-spring cascade mirror, this is going to be the smallest you can get away with, which is an effective voltage across the bottom transistor. So that means that the voltage here is an effective voltage. On the source, we need to have two effective voltages now. That's the smallest voltage we allow on the source. So the gate here will then be two effective voltages minus one effective voltage minus a threshold voltage, which is the difference between a threshold and effective voltage below the negative power supply.
Two effective voltages because of that current source?
You've got an effective voltage here. No, not because of current source, because of one effective voltage across here and one across here.
Yeah.
Yeah. Yeah. Okie dokie. So what else can we do? I think I'm going to, I'm going to take a copy of this. So I just want a black bit. Yeah? I think I can save time. I don't know if I can save time. Should probably just draw it again. No, that doesn't work for me. Come on, how hard can it be? Come on. No. Oh, you can't see what I'm doing there. I'm trying to get a copy. Oh, there we go. All right. Okay, so let's get rid of most of all of this.
How low?
Okay, so if you think about how is it that we make high gain amplifiers, OTAs, whatever, then it's about taking a current and dumping it into a high impedance node. If that node impedance is high, we get a high gain. If we make it very high, we can get a very high gain. So if you go back and you think about what are the current mirrors, the cascodes that we looked at last time, we can actually make the cascode even better than what we have here with a constant gate bias. Because we can pop in an amplifier around that structure. So putting in the B1 here and another amplifier up here, minus plus the B2. Okay. Now when we do that, then we increase the output impedance by the gain of this amplifier. Well, that's what happened when we used that super cascade, whatever, last time. So that means that the output impedance have increased by that, which means that the gain has increased by that amount. So now we get a gain, which is going to be GM, and then times RDS, GM, RDS. That's from the cascade structure here. But then we're going to multiply that also by the gain of this amplifier. Yeah, like that, times probably 1 plus A, like that. And A is probably going to be GM RDS. We want to have a simple amplifier. So that one there is probably in the order of GM RDS. Maybe there's probably a half on it somewhere. Let me just put a half on. But now what you can see is that we have essentially going, by putting in that, we have a gain which is the order of GM/RDS times GM/RDS times GM/RDS. It's something like GM/RDS cubed now. Okay, maybe that's a half, and maybe that's another half of the amplifier. Something like that. And this is still, in principle, a single stage amplifier, because the gain only happens in that point there. Yeah. You might want to put in same gain structures here, I don't know, everywhere if you like. But this is actually a pretty good amplifier as well for that. You get a really quite decent gain without much headroom doing it like that.
So the reason why I haven't seen this before with the gain stage amplifier. Like a lot of textbooks, I guess those aren't real world circuits, but with most real world circuits have this sort of.
This is an excellent amplifier, so yeah, you could for on-chip circuit, absolutely you could.
A lot of the papers and stuff I read, they just have VD that don't drive the gates.
Yeah, but driving the gates give you better control and give you a high output impedance. Yeah, some of it depends on the. And do you really need that much gain? A kind of a question that's important to ask yourself, because in most cases what you do is you operate up at the. If you look at an op amp, output characteristic or transfer characteristic, it looks like that. Yeah, so gain and frequency, log plot. Yeah? So normally, if you have a lot of gain, this is a fairly low frequency pole, which means that you normally operate up in this area here, which means that, well, actually, the DC gain is not really that important. What is important is what your gain bandwidth is, because you probably don't spend a lot of time at DC. You might spend a lot of time up here where your signals are, but that depends on the application. Yeah. But sometimes, especially if you go short line width, so if GM/RDS is not very good, if GM/RDS is say 22 nanometers for instance, GM/RDS might be like 10. Then having 2 stages so you can get like 100 times gain in the op amp is kind of pushing it, calling it an op amp. You probably want to have a DC gain of about 1,000, I'd say, so 60 dB before you can really say, oh yeah, this is a decent op amp. Yeah. 120 dB is better, but 40 dB is not very good for an op amp. So you might want to put in some more gain stages, even for that. All right. Okay, so what else should we talk about? I do want to talk about another thing that we can do in the gain stage. So I should have taken another copy. This was too messy. Okay. So what I've been talking about so far is a single stage amplifier and the OTA. But of course, sometimes you do need to drive a load which is not capacitance. You need to have a resistive load at the output. And when you do that, then you've got to put an output stage on. Now, you could put a common source at the output. The trouble with putting a common source at the output is that it takes a lot of voltage. You lose a threshold voltage. If you want to make it symmetrical, you lose 2 threshold voltages. Even at a 1.8 volt power supply, 2 threshold voltages might still be like, 1.2 volt or something like that. So well over half your supply voltage. That might not be acceptable. What you can do instead is to put in an output stage where you try to, not using a common source, but not a common drain, but a common source type amplifier stage. Okay, because the this structure here, you can pull all the way to ground and all the way to VDD if you have an N at the bottom and a P at the top. The trouble is that now you have a common source stage, and that gives you gain, and you've got to bias it. So one way that you can bias it is by putting in a couple of transistors. Because it's a very neat circuit here. So you put in 2 transistors like that, and you bias it like that. So that's VB1 and VB2 here. So in terms of what happens from the current source side here, you don't really change the impedance level in this node here. They're still depending on the impedance in the 2 output branches of these current mirrors. So you don't really change what happens on these nodes as such in terms of what the voltage swings are. Well, what you do change is where the bias point lie. Because what you can do is you can choose the voltage here by this bias voltage. So the voltage bias on the gate here, you can choose it to be anything really, just as long as you keep these 2 in saturation. Now you normally want to bias it in such a way that you just turn this one on here. And you bias this one here by this essentially source follower, if you like. So this is just turned on. So you have some current flowing in there, but not too much. So then what's going to happen if you push current into this node here, this node voltage here will rise up, and that is going to cause an increase in current here. That's going to drag this node voltage up here. So if you push current into this node, both of these nodes here is going to they're going to go together, and they're going to be pushed up very high. So that means that can go pretty close to the power, really can actually reach the power supply. So you can turn this one here off and have a very large gate source voltage on the N transistor there, which means that you can draw a lot of current in there. You can easily draw a resistive load now. So this is a good sort of low output impedance output stage. That is rail to rail. Obviously, you can also do. You should also be able to put that rail to rail output stage. Yeah, you can put it on here as well. Same thing. We put that bias circuit in here, and then we have a rail to rail output stage and a rail to rail input stage. So now we have a rail to rail amplifier. That's certainly also possible to do. So yeah, that's rail to rail output. Now it is a common source stage, so now you have 2 amplifier stages, so you've got to put in Miller compensation. Often you put it into this point here, or you could put it really anywhere in the stack here. It's not so important. If you put it into that, you might get a free lead compensation from 100GM for that one there. But yeah, it becomes more complicated. It can be unstable because now it's a 2-stage amplifier. Even if the gain of the second stage is not necessarily high, you don't put in the second stage to get gain, you just get it to get the drive capability sitting up there. All right, so how much time have we got left? 45 minutes, 40 minutes. Okay. Yeah, let's see. I think that's all I want to say for these different amplifiers. So the cascodes, telescopic cascode or current mirror amplifier, the Foley cascode, rail to rail input, and the buffer stage at the output. So those are really quite important tools to have. And you'll probably, when you read papers, you're going to see references to these circuits a lot. Okay, got to change to the next topic now. So, done with that. Okay. All right. I need to current mirror op amp again. See if it's still there. There we go. Okay, so the next thing I want to talk about is fully differential op amps. I don't know if this was properly faster. Okay, I do need to put in some cascade. Yeah, I do need to put in some cascodes. Here. Okay. Whoopsie. Not going to go to the job of this. Okay, let's try to reconstruct this one here. And then I do want to have a cascode at the output as well. Oh, sorry, so the other side here. So I'll get rid of this line here, and I've got to put in a cascode at this stage here. So this is now, again, VB1 over there. And then we have the cascode like that, which is VB2. Okay, so this would be I haven't really changed the circuit. I just put in a couple of cascodes that we know is better. Okay. Now, we probably know that fully differential circuit is better than single-ended circuits. Now, fully differential circuit is better because you get twice the voltage swing from that, because if you have two output nodes, they can swing between the two power supplies, then you can essentially have plus VDD and minus VDD at the output, whereas here we can only have VDD to ground. So we get twice the voltage swing, which is a good idea, especially if your power supply is low. That's really important to get more voltage swing. The other thing that's important from that perspective is that you get much better common mode rejection. If you have something that's symmetrical, maybe the common mode changes at the output, but if it's in principle a fully differential, a fully symmetrical circuit, the common mode rejection is going to be better. Ideally, it's infinite, but due to mismatch, it's not going to be infinite. You also get better noise immunity because many signals are coupled in as common mode. So because you have better common mode rejection, then you're rejecting noise coming into this is much better. So fully differential is really just better. Even from a power point of view, depending on how you normalize things, to get the same signal swing and bandwidth or whatever, you can actually noise, to get larger outputs when you can run it at lower current, you can actually get a power improvement. So reducing power consumption by making things fully differential, even if it doesn't look like it, because now you have two signal paths instead of one. Can actually do that, depending on how you normalize things. All right. So fully differential is really important. Now, how do you do a fully differential op amp? Probably the easiest thing is to start with this circuit here and make one change. All you need to do is to delete that wire there. Now it's fully differential. Oh, that was easy, wasn't it? So now we have two outputs. Have another output over here. We should probably put a load capacitors on here. CL. And if this is the positive input and the negative input there, then that becomes V out plus, and this becomes V out minus. If that's right, I think that's right. It's going like that. Well, kind of over here. Should be. Okay. Now we're left with something though, because at the moment I've been very naughty, okay? Because I have left that gate there disconnected. Now, if I ever see a circuit like that with a gate disconnected in any of the assessment material, I know you haven't done your simulation properly, because this doesn't work. You can never ever do that. You cannot leave a gate disconnected. So we do need it for something. I'm going to. The first thing we could do is to just, bias it with a constant voltage. Now we come to a question. Now, if we do that, then the current that we have flowing here, let's call it. Let's just make it symmetrical. Let's make this one here the bias current. If we have a 1-to-1 current mirror up here, then what we want, the bias current is half times the bias current there, and half times the bias current there. So what we've got to do is we've got to choose the voltage on that node so that we have half times the bias current. But now we get into the problem that you said, that was mentioned in the book. Now we actually have essentially what is the current source up here and a current source down here. And if they are not identical, not similar, identical, then this node is going to be, let's say the bottom one is a little bit larger, this node is just going to go slam and cause this to go out of saturation into the triode region. It's not operating properly any longer. See, this is now a problem. Now if you go back to this circuit here, we have something similar, but if the current up here is larger than the current down here, so we have a current flowing out here, then it pulls down like that. Effectively what it does is that that gives us an offset output current. Now, the way we normally model that is referring that back to the input, saying, well, actually, we just compensate for that by having slight different input voltages, and that's the offset error. So if we have and there's a feedback from that pass back to the input, so it still works like that because we have the feedback. However, if we look at how to make a fully differential circuit up here, where would you go? Here. A fully differential circuit, let me just scribble this down here. This would look like, I'm using resistors here. Probably this would be capacitors, but what you do with a fully differential circuit is that the feedback mechanism is differential. It's got to be completely symmetrical. So you look at the difference at the output and you feed back that difference to the difference of the input. It doesn't say anything about what the actual voltage is. Okay? So both at the input and the output we have the common mode and you have a differential. We are feeding back, the feedback is in the differential. The common mode can be anything. And if there is a difference in this current source and that current source, then the common mode is going to be probably sitting right at a negative supply, or at the positive supply. And it's not sitting right in the middle to work properly. So the way that you normally address this is to have another feedback loop that looks at the common mode signals, and you feed back the common mode signals and make sure that the common mode is then sitting in the right spot. how do we do that? We sense the output voltage, and the two output voltages. Actually, probably right. Yeah. So the two output voltages goes into what's called a common mode feedback circuit that then drives this voltage here. So common mode feedback, like that. So now how do we do that? Well, essentially what we do is so the common mode feedback, it'll take the common mode. What is the common mode? That's V out plus V out minus on 2. That's the common mode. And we compare that with a desired voltage. So VCM target, whatever, like that. So that's the kind of voltage we want to feed back to the system in here. Yeah. So the first thing is how do we measure the common mode? Well, let's go here. So the easiest thing to do is you have V out plus and V out minus. You can put in two resistors like that. Okay, so this is going to be the average. If these are both R, that is going to be the average of the two. Yeah? And then what you do is you compare that with your common mode reference. Let's call it common mode reference, probably better. A CM reference. Like that. You compare that with that, put it into a differential amplifier, and then that becomes your common mode feedback circuit. So V common mode feedback. That's that line there. That's V common mode feedback. Now you need to make sure, I haven't put plus and minus on this differential amplifier yet. It's not because I'm not committed, because that's important. I just want to make sure that I do it in the right spot. So let's see what we have now. If we drive the common mode feedback here, if we increase this voltage here, if that goes up, we will pull more current down here and more current down here, which means that those two output voltages will both drop. So we're reducing the common mode voltage if we're increasing this voltage. Now, if this, we can make a symmetrical op amp where this sits at the top, that would be different then. But for this circuit here, if we increase this voltage, the common mode will reduce. So going back down here, if this is large and we want, let me put in plus minus and see if it's correct. Okay. I see. So if the common mode here is larger than what we want, then this will go up. So we're increasing that, which means that we pull it back down again. So that should be correct with that sign. Yeah? Okay. I'll try to be smart and work backwards, but I couldn't work it out. Okay. Okay. Now that amplifier there doesn't need to be complicated. In fact, having a simple amplifier is really quite good. I would probably make the amplifier here a differential pair, PMOS differential pair like that. And then one of them I'll just dump to ground, the other one I'll put into a diode connected transistor, like that, and that will be my common mode feedback like that. So then what is plus? If this is higher, that's going to be plus and minus like that. Okay. You'll see in some papers what they put in is, instead of having just a diode-connected transistor there, they have they put in a current mirror load from this differential pair. I don't like doing that. Now, the reason I don't like doing that is that it's not critical if the common mode. Oh, how should I say this? The amount that the common mode changes. Yeah, sorry. I have to think. What it is I really want to say. So the amount that the common mode changes around depends on the gain in the common mode feedback loop. So the higher the gain in the common mode feedback loop, the more stable it's going to be. So the amount it changes from natural point is that change divided by the feedback loop. Now it doesn't actually matter so much if the common mode wobbles around a little bit. That's not critical. What you want to make sure is it kind of sits round about the target, which is probably half your power supply. Yeah? Well, it should sit around there. If it wobbles up and down a little bit, it's not actually very important. What is important, though, is that we have introduced another feedback loop. We measure in this, and then we feed that back into this loop here. Now, if that is unstable, that's not good, because now the common mode will wobble up and down, and that, if it's unstable, it'll become larger and larger. Now the common mode just flaps between the power supply. See, that's no good. So it's really important that common mode feedback loop is stable. Now, already you have the load capacitors here, which act as your compensation capacitors for your feed forward. In principle, you could put them between the two outputs. That would stabilize the differential feedback. But if you put them between the two outputs and save capacitance, then the common mode loop has no compensation capacitor. So it's much better to have load capacitance to ground at both of them, because now those load capacitors will also serve as compensation capacitors for the common mode feedback loop. Now, you already have pretty good gain. From here to the output, you've got the same gain really as you have from a diff pair to the output. So you don't want to put more gain in the common mode feedback loop, because now you just risk making that loop unstable because you're putting in more gain, but you're not doing anything to the compensation. So for that reason, I do not like to do anything in the common mode feedback that adds extra gain, which is why I like it to do like this. It doesn't need to have gain. You just need to take the difference. There's enough gain already in this system. All right. I want to say one extra thing about the common mode feedback. So I'd show you the easiest way that you can measure the common mode is just two resistors between them. However, I have now broken the op amp. Because I have put a resistor between these two outputs. And that means that from a differential purpose, I have now dropped the impedance down in this. The differential impedance now, the series resistance of those two. So unless I make those two resistors like, hundreds of megaohms, something like that, this is not good, especially if I have the super gain stage at the output, like a really, really high output impedance. If I put in those resistors, my gain is just dropped down to nothing. So that's not good. There's a number of different ways that you can address this. I think probably my preferred way is just to put in a source follower to drive those resistors. Okay, it's fine. You're going to lose a little bit of range, but not very much. So if you look at having, we've got to have a differential pair to compare the common mode with the target common mode. So with a PMOS input pair here, we've got to have a voltage which is kind of lower than mid-range anyway. We lose a threshold voltage this way. So if we use an N pair to shift it up first, we can shift it down again. So we're not actually losing. We're losing a threshold voltage involved swing at the output, but it's not too detrimental. So I will put in space on this page. Sorry, I've got to move this down a little bit. Come on. Yeah. Okay. All right. So I put in a voltage follower by squeezing it in here. So, oh no, not like that. Too much. Move this out here. Oh no. More precise here. Okay. So putting an NMOS voltage follower. Oops, I can't go on that. It's the wrong place for the current source. Current source down here. Like that. And the same for this one here. So now I have fixed the problem I introduced. There's other ways you can do it. There's circuit that uses a differential pair directly at that point there. Now you've got to be a little bit careful with doing that because you need to make sure that that differential pair doesn't saturate. Because as soon as it saturates, you lose the common mode feedback. So I think this is a better solution if you have resistors. Okay, common mode, full differential. I think that is it. Yeah, I should probably say that when you read papers, sometimes you see that they have shown a circuit diagram, and then in some line someone says, "Oh, by the way, this is actually implemented fully differential on the chip," but and they just leave it like that. Yeah, so you might not see that they do it fully differential, even if they don't. If they do. It's left as an exercise for the reader to transform it into a fully differential circuit. Okay. Any questions to the fully diff? Any amplifier can make fully differential, any structure, really. Just taking out the asymmetry becomes fully differential, really. So.
Does the common mode feedback depend on the output swing? Like, I'm just thinking, you're saying that it doesn't need to be that great, but like if your output is like very quickly swinging between high and low, will that change your common mode then?
So hopefully, well, yeah, okay, it probably will. So if you swing very fast, you probably don't have the same. You don't have complete symmetry in the pull down and pull up. So if it swings very fast, it might swing faster lower than it swings high, the other one, which means that the common mode will now have to try to fix that sitting in there. So the bandwidth of the common mode is important. Yeah, you can't have something that is really slow.
Yeah, and what doesn't matter if it's rippling? Like I thought, like common mode, and that's why we really want high common mode rejection, and like having our output ripple seems like a really bad thing.
Yeah, but the output is the difference between the two. So if the output goes like that, it doesn't change the signal. It's the same reason that the fully differential is good to reject noise coming in, because it doesn't because noise is often injected as a common mode. Yeah? So that causes both of the output to go like that. It doesn't matter. Yeah? So, but yeah, what matters is that if it oscillates. Now that is bad. Yeah? That's more important than trying to keep it dead stable, which is why I don't like to add extra gain in that loop. Yeah. Okay. Oh, I might need at least 15 minutes for the last bit.
Are all these current sources free?
Hmm?
Are all these current sources? Is it okay if we have all these current sources now?
Current sources is just generated by current mirrors.
Yeah.
Yeah. But I'm glad you asked that question because how do you make a current reference?
Isn't that supplied as an input to the chip?
When was the last time you used an op amp in a lab? This morning, how many pins did it have? How many of them are current inputs? Ah, okay, here you go. You've got to build it on chips. Now, normally you make the assumption when you make a chip, it's not normally an op-amp, it's normally like a system on chip, whatever. All your circuits, all the analog circuits need a current reference. So you have someone make that current reference for you, and then you just take copies of it with current mirrors. Right? So it's on chip. So when you make a circuit which is part of a larger chip, you can normally assume that it's a current reference available to you. But if you make the whole chip, then someone got to make that, and now you've got to make it. Yeah? So it's not normally part of the design task. I'll give you that. I'll give you a current source, but if you make a chip, you've got to have it. You can take it off chip. It's good for test chips to take it off chip so you can control it. But if you make a production chip, you want to have it on chip for sure. Yeah. Okay. I'll show you the yeah, maybe I do this version here. So this is a typical current reference circuit. Is very commonly used. You can embellish on it with putting in cascodes and all that usual jazz. That's not so important. But this is the main circuit here. So you've got your two current mirrors sitting like this, or kind of current mirrors. You have that one up here. Okay, and this is normally a one-to-one current mirror. Now, this is a it's a very common current reference to use. Now, what you've got to have, if you have a one-to-one current mirror up here, that tries to keep the two currents in these branches the same. If you want to have the two current branches the same in this one here, you've got to make that transistor wider than this one because that transistor has a smaller gate source voltage than this one over here. Because we drop the gate source voltage from here is dropped down a little bit to give this one here. So this one here, the bottom has to be 1 to K. Okay. Now, I really wish we have time to analyze this. I think you should do it yourself. But if you make the assumption that the two currents here, I1, flows in both these branches here, and you have R there, and then what you can find is that transistor 1 here, GM1, for K equal to 4, GM1 is going to be equal to 1 divided by R. Now, that is important because what you can do now is that you can use this one here as the output and have lots of current mirrors hanging off here to do your biasing. And if you derive all of your currents from this source here, you know how the transconductance scales with current and how the transconductance scales with transistor dimensions. Then you can get all your GMs in your circuit to track that resistor. If you do it in weak inversion, you can also do that. Then the GM becomes ln k times ln k divided by R. Try to analyze in weak inversion and strong inversion, and you'll find that. Now, the reason this is such an important reference circuit is that GM is really what matters in terms of stability, in terms of speed, in terms of noise, in terms of pretty much anything that goes in the analog circuit. You really want to control GM. So it's actually better to control GM than it is to control the current. Well, whatever you put in there, you could. If you put something in there that's not a resistor, if you use a transistor, for instance, and make it into a resistor, then the variation in what you get is going to scale with that. So, so putting in a resistor, you really want something that's temperature independent, preferably. So you can make that resistor out of a series resistor of positive and negative temperature coefficient resistors to cancel temperature coefficient. That is sometimes done. You normally have both on chip. It's quite common. So you can do that. Probably the main problem with this approach is that the normal variation of the resistance is, it's probably about plus minus 20%, something like that. But it's not necessarily acceptable. And if that's not acceptable, well, you can do two things. You can either, oh geez, excuse me. You can either put this off chip as a reference resistor. That's perfectly fine. Your op-amp didn't have an off-chip resistor, I don't think, because that would be annoying. So you can do it, and for test circuit it's good, but for production, your manager would not be happy if you say, oh well, I need an off-chip resistor. Okay, you might be out of a job. So what you can also do is you can have trimming. There's another thing we need to talk about for that circuit there, but trimming is important. And it's not very hard actually to do trimming. All you do is to have a resistor here, a number of series resistance like this, and this might be so if you have a variation of say 20%, then I probably want to make this one here something like R on 5, and then R on 2 times 5, and R on 4 times 5, and so forth. Yeah? And then what I can do is I put in transistors here that I can short out any of those ones here. So this now, B0, B1, B2. Okay, so these are just switches. So what I can do now is I can digitally calibrate or trim these resistors. You can make it in many different ways. This is just a digipot. Yeah? So you put a digipot in instead of your resistor, and then you trim it in such a way that you get the value that you like. Now you don't need to have the entire range, because you just need to rein in the process variation that you have. So if you look at plus minus 20%, you need to be able to, okay, this can only go up. All right, okay, I'll do that. Yeah, I should resync those values. It should be R minus, it should probably be R I think the top one should be that minus, so you make it deliberately smaller by 20%, and then you add them all up, so you can do plus minus 20%. Now okay, so you do have, you have just kicked the can down the road a little bit here, because instead of having the right resistor, you're just saying, oh well, we've got to fix it in digital. But this is a common analog trick. So just be quiet about this. If you can't do it in analog, you put it into the digital domain and say, you fix it. And then they will say, well, I'll do that. And then actually it turns out that they fix it almost. And they say, well, just put it into software. Okay? That's how the world works. Well-known fact. Anyway, where you put this calibration information is important. You can put it on pins on the chip. You can put it as blow up or fuses, one-time programmable memory. You can be a part of an off-chip E-square problem that you might have anyway. You just, at boot up, you just pop in the right calibration data. There's many ways you can do it in your system. It's not actually uncommon to need to do stuff like that. Yeah, but it has a cost. Yeah. All right. Okay. I should say on your op-amp, normally you just live with the process variation.
Yeah.
And do that, and then just, sometimes the biasing circuit is even just a resistor to the power supply. It's pretty simple, but it does mean that the variation in the op-amp performance is actually very large. Yeah. Okay. Okay. Now we're streaming. How are we going else? Got that. Yeah. Okay. All right, I should probably also talk about bank of references, but we're running out of time. I want to say another thing about this one here, actually, what is important, and that is that this circuit in itself actually have two stable states. You've got one stable state where you've got 0 volts here and here, so there's no current. And you've got VDD on this node here, so there's no current. This might actually be the natural state that it boots up in. Because you might, as I said, what you probably do is to have a lot of transistors that hangs on this node here to bias all the current sources. It means that you have a very large capacitance to ground on this node. You might also use these PMOS devices to bias your PE devices, which means that you have a very large capacitance to VDD on that node. So if you take the power supply, you power your chip, you move VDD away from ground like that. This node here will just stay at VDD, this one node here will stay at ground, and it's no current flowing in it. So that's no good. And that's the natural way that it's going to boot up. So normally with this circuit, you have to put in a startup circuit. You've got to detect the condition that there's no current flowing in this. We've got to do something about it. One way, you can do it in many different ways. One way you can do it is you can have a PMOS device here that you've really, it's always on, but it's very long. So it's kind of acts like a resistor, and then you look at this voltage here. Okay, so if the voltage on this transistor here, if this is at ground, so it's not started up, then the PMOS up here is going to pull this node up to the power supply. And if this turns on, then you want this node here to be pulled all the way down to ground. So this has to be very weak and long transistor. So now you have a digital signal that detects the state of it being wrong. If it's high, it's wrong. So we can put in, you can just pull out current somewhere, maybe like this. In this node here, for instance, there's many ways you can do it. So if this is high, this is logic state that says it's off. So that's high. We now pull out current in this current mirror here. That's going to force current in, so that is going to boost this up, and the positive feedback is going to keep it going. This is going to go high, pull this node down, that's going to go off. So that is a very common way to deal with that problem. So startup circuit. You can also make a startup circuit that doesn't use static power. This does use static power because you have, when this turns on, you have current flowing in that branch there. I don't think it's important because you have current flowing in these branches anyway, so it probably doesn't add very much to the overall power consumption of the circuit. But you can make a dynamic one. I haven't never had the guts to do a dynamic one, but my students have more guts than I have, so I have seen it and it works fine. You can replace a pull-up with a capacitor essentially. Okay. All right, look, I think we've got to say that's it. So I did want to have a look at current reference and bandgap reference, but yeah, I don't think we have time for it. So let's have a break here, and then we meet again in 10 minutes and do the paper. Well, let's meet. Yeah, in 10 minutes. 24-2.
Kofi Makinoa, Taekwon Jang, ETH, True Ball from UC, Davis, I think. I'll send it to you, also if you haven't.
Yes, okay. So is that IEEE magazine or something?
Yeah. It's like a conversational piece, but I found it really cool.
Yeah.
It's sort of
What you should do is to look up Rasavi's, if you haven't done it yet, Circuits for Every Season.
yeah. Apparently
It's got like it's like 20 articles, and they're all really good and they're all really important. Yeah. Yeah. Okay. So your circuit? I haven't tested that yet. No. Yeah. I will. I haven't had time. What's the lower cutoff frequency on that?
It's about 11, 12 hertz.
Okay. Six to be at 10 hertz.
Yeah. But it should be like around 40.
Yeah. Okay. Yeah. No, sorry, I haven't had time yet, but I will.
I'm curious about for Casco. You say that the current output is going to be very low compared to like this one.
No. The current output is going to be the same. Yeah. So this is. So here the current flows in here flows directly to the output. Whereas over here, the current flows in here flows through current mirrors first. So what you can do is you can scale the current. You can make that as you want to K current mirrors. So you can scale up the current, but that uses more current than this branch here. Yeah? So the idea with the main idea with this is because it doesn't matter how much current flow here in this part of the amplifier. No matter how much current flow here, all of that signal current makes it to the output. Yeah? Because it doesn't go through the current mirror, which means that you can put most of your current in the diff pair. Now, if you put most of the current in the diff pair here, you've got to scale down this current. Yeah. And now, if you scale down this current, you get a small current over here. If you have the same total amount of current in the amplifier. Yeah? So for the same total amount of current that you have, this will be better for speed because you can scale up here, but then you have not very much current in the diff pair, which means that the noise is poor. But you have a lot of current in the output, which means that you can drive a lot of current. Oh yeah, because what I did say in terms of the bias current that you have here, if you put most of the current over here, the bias current here is going to be low, which means that is not going to be very good at driving a load capacitance, on a slewing condition. Yeah. So yeah.
Basically, we cannot write a log with this one, but like, can we just jump it current at the output side?
A current multiplier. You can put on, I don't know if I would put in a current multiplier. If you need to drive a large amount of current at the output, I would probably put in a voltage buffer. Yeah. Yeah.
We could solve that issue. Maybe this simple thing.
So what do you mean?
The reason you have the second key to solve the problem.
No. This is rail-to-rail input. The 2-diff pair is rail-to-rail input. Yeah.
Increase the drain current to reduce the thermal noise for most flights.
Increasing the drain current will reduce the thermal noise.
For the most
Yes. No.
That's the reason why we just reduce.
Yeah. It depends on how you do it. So if you
Because based on the formula, I think it's something like
so a transistor here, a noise model for the drain current noise here. This is for K, gamma, G. Yeah?
if you increase that, increase the share.
Well, that depends on what it is that you're interested in. Yeah? So, in most cases, your input comes at the gate. So you should really move that onto the gate. So what you can do is you can make an input noise here, which is now 4kT gamma 1 on GM. Because the gain from here to here, this is amp squared per hertz.
So
yeah?
you mean like increase
So-
the drain current will reduce the input referred voltage noise. That's your point.
Yeah. What is what in an op amp, the input referred voltage noise is normally what matters. But it depends on the circuit, because if what you have is that your input goes into the source, then you want to have a lower current, because now this matters. So if this is your input, then you've got to lower the drain current. If
That's why it's a secondary part. All of the stage should be because
no, output state doesn't matter. The input matters for the noise. If your input stage looks like this, you have a current input that goes into the source, then that is you get this current here. That's the noise, and you want to keep this low, so you want to reduce the current here.
Because after this, this situation, you have that line, you have floated the output state.
Yeah, but the output doesn't matter because you have gain from the input to the output. If you design your op amp properly, then the dominating noise source is your differential pair. If that's not the case, that's because you have not done it correct.
Normally,
Yeah.
normally like for signal to noise ratio, it doesn't count the amplifier stage noise as small as possible.
Yeah. That's right. So you put in gain as soon as you can. Then when you have gain, then the noise becomes less of a problem in the later stages. Yeah.
Actually, I think you also make the second stage GM smaller as well because you make the input stage.
Yeah, so that's normally what you have to do. So if you go and you look at so you look at the noise from this one here. If you look at what comes up to the output, so the noise from these transistors here, they have the same amount of gain to the output as this one here. So the gain from here to the output is GM for that one. The gain from here to the output is GM for this one. The gain from here to the output is GM for that one. Or maybe the gain ratio between here. Yeah, so what you want to have good noise performance is if you want to have the GM for this one here, it needs to be large compared with this GM.
So actually, this value should be, so the K value should be very small, as just said.
Well, the K value is not depending on the GM that you have. You know, you can have a large K with a large GM, or vice versa. So, yeah, so you can decide them independently. But using the aspect ratio of the transistors, yeah, yeah. So,
And actually, especially depends on the K value.
yeah, and it also depends on where you go weak inversion. If you go weak inversion, then the GM depends on the K value, you know, because then it's just proportional to the current, and then there's nothing you can do. So, going weak inversion is not a good idea because then GM for these two is going to be the same, which means that the noise contribution for these two is the same. So it's much better to keep these in strong inversion. This is good for weak inversion because you have high GM for the amount of current you have. So that's good. But this one here shouldn't. Yeah.
Okay, another question is, if without the external feedback, the single element only will be on without any external feedback.
Oh yes.
Because asymmetrical.
Oh, it's offset errors and stuff. You know, you can't use an op amp without feedback.
But for normal, even for normal op-amp, just a voltage op-amp, it's just like a comparison.
Then it's just a comparison. Yeah, that's right. So, kind of. Okay, let's do the paper. So whose turn is it to do the paper? Yep. Okay. Oh. Oh. There you go.
Yeah, it was just this like sinking realization, like you might misunderstand as possible things just talking
All right, let's go.
But then nobody
Hello everyone. Today we discuss about the CMOS digital phase OTA, and OTA is a we cover about in today's lecture. And the background of this paper is that it's a rapid Bluetooth output IoT device system requires to have high performance and low power consumption for the energy harvest and powering small batteries. However, the performance of the conventional analog digital circuits often structures to meet demand under the low voltage conditions, especially for the key components such as the OTA, operational tram conductance amplifiers. So this paper mainly shows that the analog circuits can leverage digital circuits technology to maintain the excellent performance despite in low voltage and power consumptions. Just this. So it shows the digital circuit-based the OTAs that use a statistical digital logic gate instead of the classic differential circuits to process the signal to get the lower consumptions. So let's pass me to introduce the circuits detail.
Okay. Here, this picture show the show the circuits, and this one is let's work for the inputs of these two differential pair. You can see here, Vin is here, and you can see VCMP here. There is I think this is a negative feedback to calibrate the VCMP and make the system stable. And you can see here the differential here. He used many calibration. I think this is to compensate for the this is to compensate for the variation, process variation by inputs different calibration word. You can calibrate the voltage here. Otherwise, it's you can see the output here is not well. But if you after you input some calibration word, the output it becomes normal, and you can see so you can see digital parts in here, here, and here. This is used I think this is to measure whether the outputs of the differential pair is correct. If it's not correct, then the feedback loop will open to calibrate the VCMP, and if the output is correct, then open the output stage and output the signal here. I think these two is source follower to a voltage follower to output stats voltage. So the main analog parts is this differential pair and this output stage, and here the common mode is chapter. Okay, and it's mentioned. It's mentioned here. It's mentioned in here the PMOS devices. The PMOS devices is mentioned here. Large area has been adopted in PMOS devices in BO1. Why we need large areas in PMOS devices? This is the first question. Okay, anyone want to answer this question? Okay, answer is, I think because the new COX in the PMOS and NMOS is different, even in the specific ratio. I think it depends on whether on process you are using, but actually the mu-CoX of PMOS is usually smaller and NMOS, and to match the two the PMOS and NMOS, you need wider PMOS, and the reason of this is the carrier in the PMOS devices is the electron pulse.
Can I just stop? So figure 1A1.
Yeah. Here.
No.
That's the one below it.
That's the one below it.
From
Figure one.
from A1.
You should not.
Yeah, it's yellow.
It's that one. It's a resistor.
Yes, it's resistor.
So the NMOS doesn't matter because they shorted it. I don't know why they drawn it like that. I think it's the.
I think he mentioned here why this PMOS why we need have a larger PMOS. The only thing I can explain is the mu-CoX is different, and to match these two devices it's need a larger area of PMOS. Otherwise,
Yeah. So matching is the Pellegrin's law is what we did
yes.
in the course earlier.
Yes.
But yeah, the matching. So they have extra lot to that resistor divider. That you're having that in the figure 1A1. They just use a
Yes,
diconnected resistor as a resistor.
They use
They want to match the two R's in both channels.
Yes, because the ratio of the resistor is important, otherwise the summing network is not correct. And also it's mentioned, you can see here, it's mentioned, you can see the frequency here. Do you think the frequency is is fast or not? I think it's not very fast because and what limits the frequency here? I think one is the combination logic in here. You need to weight the combination logic, and also you can see calibration here. These circuits use the charge and discharge the capacitor to calibrate the VCMP, and but charge and discharge actually it's need time and these two can't go parallel, it goes series. So the delay is the delay of the combination logic at the charge and the discharge time. And I think this is the main limitation of the frequency. And you can check here. It's need to wait the VCMP until it works. And yeah. Also, and that's all things I want to talk about in the circuits that are about these circuits, and then let's move to the simulation results.
under the big margin. Modifier will be about 65 or 16